Welcome back to Learning Solidity. In today's tutorial I'm going to be covering a topic again which has been cropping up very frequently, and that is to do with nested arrays, or the inability to use nested arrays. Before I actually jump into the tutorial, I want to highlight I've added a new section to the Learning Solidity repository on GitHub, which is called Support. Now the reason I'm highlighting this is because I'm actually basing today's tutorial off sort of an article or document that I'm actually going to produce later to correspond to this video. Now I have already done one which is called Invalid Implicit Conversion of Arrays from Storage to Memory and Vice Versa, which is going to have a few references in today's video. Now what it is essentially I've identified a kind of an issue or a very common trending theme where people are struggling, and I go into a little bit of depth with it in regards to looking at the types of errors, looking at sort of memory layouts, looking at the different ways you can actually sort of approach the issue, looking at alternative mechanisms. For instance, this way I'm talking about storage and memory. This will tip over today's tutorial quite frequently because it's very relevant to nested arrays. I look at how the different ways that values get stored in the storage, how to access them. I look at the memory and the problems you will have with memory, and essentially just a very sort of rounded investigation on the problem, and just to try and sort of make it clearer for the Solidity community to sort of get past these sort of little humps while we're in the early stages of Solidity. I also do want to just say kind of thank you, and I've also left a little note at the bottom of the Solidity README, which was to Nikita for identifying a safe math bug problem on tutorial 11, which was an issue, and he put a pull request on for it, and it is now resolved. So let's get back into today's tutorial. So you're obviously here because you're having problems with nested arrays, or you obviously just like to follow my videos. Well, nested arrays is incomplete. It's the easiest way to put it. It's not been fully finished, and the easiest way to kind of prove this is to show you an example of where a nested array just simply does not work. Okay, so there's a little bit more to it than this, but I just want to highlight to you to the point that nested arrays are incomplete. So let's just create a function called getArray, and we're going to pass in a uint. It's nested array. Just call it p, and it's public. And there we have it. Okay, so we can't create it. And we can't create it for the reason, if you go to the compiler, unimplemented feature error, nested arrays not yet implemented. So they haven't actually even implemented that functionality yet. Now, when you see that error, you might think, oh, I just can't use nested arrays. That's not entirely true. You can use nested arrays, just not in the way that I'm showing you here. Now, what I'm actually showing you here is nested arrays interacting with the call data. Now, there's essentially 4 ways you can store data within Solidity. One's not really a data storage, it's more a temporary storage, and again, well, technically 3 of them are temporary storage, and one's only sort of persistent storage. You have what's known as storage, which is data that's retained on the blockchain itself, and that is the only persistent storage mechanism that you really have within Solidity. You then have memory storage, which is basically created on the point of your interaction with the contract, but also destroyed at the end of your interaction. So that is a very volatile sort of level of memory. It's a very volatile level of storage. So if you wanted something for long term, I wouldn't store it in memory. Then you have the call data. Now the call data is actually stored as part of the transaction, and that is the data sent from the person interacting with the contract, and also the data that's sent back from the contract to the client or the address. And the final bit, and the final way you could store any sort of memory or data within Solidity is the stack. Now stack is very, very short-lived. It basically gets stored in the stack. Once the operation is finished, it can be just instantly removed from the stack. So don't rely on those mechanisms if you want long-term persistent storage. Just stick with what's known as storage. So in this example we have here, we are using the _p variable, which is the nested array of uint, as a parameter being passed in from what would be an external sort of source. So that means it has to come from call data. I can show you this fixed in a sense of, instead of it being public, let's make it internal. Now there we have, it's now not erroring anymore and will actually let us to compile it, but we can't interact with it externally because it's no longer accessible. So because we've made this internal, it's then no longer depending on the call data, and therefore we can now use it. So the next thing we can kind of look at as well in regards to this, let's just go back and make this public again. Let's also get rid of this parameter, and instead now what we're going to do is return a uint, which is also nested. Now again we get the same thing. Unimplemented feature error, nested dynamic arrays not implemented here. So again, because we're interacting with the call data, we can't do this. So again, if we change this to internal, this resolves the error. So that is the simple way of understanding the unimplemented nested arrays. Now I know a lot of you are thinking, yeah, that applies to a nested array in the way that you're defining it there. Actually not entirely true. That applies to sort of that scenario because uint is a primitive data type. Now a lot of the ways I've seen people complain about this is that they'll do something like this, and let's make that public again, where you have an array of strings, and you're probably sitting there thinking, nested dynamic arrays not implemented here. What do you mean nested dynamic arrays? It's a string. Well, a string is not a primitive data type. It's an object or a structure, and as part of that structure you have a character array. Now I can show you some little illustrations I kind of have here ready for this tutorial. Now let's skip along to a string. Okay, so with our string, this is what string data looks like. It's essentially a length with basically an array of values, and that's why you actually have this whole concept of a nested array. You're creating an array of strings, and a string itself is an array. So that is where your nested array comes from, and that's why you can't use an array of strings of being passed in or returned, because it's simply in essence an array. So that obviously applies in that way as it does with passing it in as a parameter as well. So if we get rid of return, again we're still getting the nested arrays not yet implemented. So obviously if I change that to a string, which is then treating it as just a standard array or a sort of one-dimensional array, that works fine. The same with returning it as well. So let's look at some cases where nested arrays do work. Okay, so we know we can't have it as return values or function parameters. Can we have it as part of the function itself? And the answer to that is yes, we can. So let's create the uint again. Let's say this is going to be stored in memory, and let's say this is our nested R. Okay, so we have a nested array in memory. Okay, great. Can we do anything with it? No, we can't. We can't do anything with that. Now, the reason that we can't do anything with that is because of how essentially an array is stored in memory. Because you basically are stating that you're using a dynamic array, you constantly have this concept of all this data stored in memory. Now, this isn't just for a two-dimensional array. If I'm correct, this also applies to a single-dimensional array. So for instance, if I just take a single-dimensional array like I have there, and let's say I want to append a value to it. Now, I can't use the push because that's not part of this, that's not an attribute as part of this sort of data type, which you might have seen previously. So the only other alternative would be to reference an explicit index, which you think, oh, it's not throwing any errors, so surely this will work. So if I create it and run it, no, I actually now get VM error, invalid opcode. The constructor should be payable if you send value. Now actually ignore that message. This is not relevant to what's going on up here at all. If I make a constructor that's payable, it won't fix this problem. So what we are having is a problem here, and this is where I'm actually going to jump into one of these documents I created. Okay, so let's have a look at the kind of way that Solidity stores memory. Now, we have this block of memory. Let's just assume this is our block of memory. first things first, we have what's known as scratch memory. This is memory that you can use freely, and you don't have to worry about it ever being overwritten, which is fine. You can use it for whatever. It's ideally meant for people writing like very short assembly, inline assembly functions or something like that, which is basically the first, if I'm correct, 64 bytes, which is, that's what this is 64? I believe that's 64. I'm not going to count it. I'm just going to assume it's correct. Then you have what's known as the free memory pointer. Now, if you've ever used Solidity assembly or seen any of my tutorials, that's essentially what msize is. When you call msize with an inline assembly, it actually looks at the value here to see what the next free memory pointer is. Now, as you can see here, we're saying it's 120, or the hexadecimal value of 120. And as you can see here, we actually use up to the hexadecimal value 11f, which that's what this value is over here. So obviously the next free value is 120. So that's always something to bear in mind. Now, I've seen some tutorials which actually, for some reason, get you to write to this actual free memory pointer. No, never write to that unless you really know what you're doing, because if you don't, you're going to have basically the rest of the functions within Solidity come along, read what that free memory pointer is. Even if it's pointing like here, it'll start writing memory to here, or even here where you actually have some other predefined sort of data structure. So unless you really know what you're doing, generally just leave the free memory pointer alone. It'll automatically get assigned, even if you're doing assembly instructions to a degree. If you're doing some inline assembly, be mindful that that might not be set correctly. I've been down this route before, and I've had an absolute headache trying to figure that one out. So let's have a look at this dynamic array in memory. Now, this is what it'd look like in memory. So we have, first things first, this first part of our memory, which is also going to be a useful example if I bring up my illustration here. Now, an array in Solidity works in a few ways. This is essentially call data array sort of structure, where you actually have this data type first, then a length, then the elements. This doesn't apply for memory or storage. In memory and storage, you only have length and then your elements. So you can completely discard the data type, which is usually your first 32 bytes, if you're handling this in storage or memory. Okay, now you generally don't have to worry about this too much in storage, because you don't have to worry about sort of memory allocation and so forth, but it's just be mindful of it when you're handling it in memory. So let's just obviously take that the first 32 bytes is going to be the length of our array. Now in this case down here, we have an example where an array equals 132. So it's a length size of 3, and that's what we should see here. Then the first element is 1, which is what we see here. Next element is 3, which is what we see here. And the next element after that is 2, which is what we see here. Now, what we're actually doing in call data is defining the data type. So as you look at the memory here, what this will be is a sequential set of values. So it won't be broken up like I have it broken up here, which I pulled from Remix. The reason for that is it can tell the Solidity compiler, okay, these set of bytes are this value, these set of bytes are this value, and so forth and so forth. As we're in Solidity and we define these constraints ourselves, so if we jump back to Remix a second, we're saying it's a uint array. We're already stating that we know it's 256 bytes. We don't really need to store it in memory, because we've already defined it within the confines of the contract. So we don't need to store it as well, because that will get basically stored as part of like the stack or so forth. So in essence, we can completely discard the actual the storage type for now. So we can see in this case that we actually have 4 values, because the first value here is 4. So that's going to be the first 32 bytes. So we've got 4 for the first 32 bytes. The next 32 bytes is a 1, so this is the value 1. So we can also see down here. Then the next 32 bytes is a value of 2, which is we see down here as well. Then 3 and 4. So that's how our array looks like in, or essentially what our array looks like in memory. Now this is kind of where we come into like, but why can't I add something to that array in memory? It's a dynamic array, why can't I just add to it? Well, the way Solidity stores a dynamic array in memory is kind of wrong in essence. It stores it in a sequential way. Now, if we look just very briefly at how this is stored in storage, I don't want to go into this too much because this is kind of getting quite complicated now, and it's easy to probably just flip through this document than it is for me to explain it. Now, what you have here is actually references. Now, as you can see, the reference point for this object here is actually the key for this object here. Now, the next reference you use is actually this key plus 1, which is what you get for this one. As you can see for the example I have down here below, all you're doing is incrementing each value by 1, and it doesn't matter where any of these land in the actual storage engine, because you're looking up based off the actual this key or this object reference. So you don't really have to have things in sequential orders, as I basically demonstrate with a little bit of inline assembly and sort of storage mechanisms here, where I just basically push the elements in random order and using different storage techniques, and then access them using the actual keys themselves and how to generate the keys. But again, I'm not going to go into that too much. But I am going to sort of address this whole concept issue. Now, this is something I did address within this document as well, which I will go into a little bit, and this obviously explains why we can't really use dynamic arrays within memory. Let's say we have this dynamic array here, which has 4 elements, and we want to add a 5th element. Okay, well, because it's stored sequentially, we have a problem now, because we have an unsigned integer sitting in our basically our order. So we've now got a problem. This unsigned integer needs to move, so we now have to move this unsigned integer. And something I actually didn't mention in this is any references to this unsigned integer also need to be updated. So somewhere we need to store all the places where this this unsigned integer is actually referenced as well, and this is where we're getting into a very complicated territory, because as you can see, essentially the process of actually doing this is to allocate a new 32 bytes of memory to the heap, move the unsigned integer forward 32 bytes, increment our array size to 5. Actually, I'm sorry, I'm not sure how well you can see this. I probably should have zoomed in there earlier. Increment our array size to 5, add our 5th element between x100 and x11f, which is what the unsigned integer is currently assigned to, and then update the free memory pointer to be at the end of not just our array but after the unsigned integer as well. So there's a lot going on there, and that's a lot of operations to our calls to our or our contract, shall I say, and this is now getting a very expensive sort of process. So that's kind of why the key reason is you can't really do much in memory with dynamic arrays, and that's the key thing to remember about this, is you're limited by the actual sort of scaling of your actual array. So again, that's essentially the big reason why you can't have dynamic arrays. So the only other way you can actually have a dynamic array within Solidity is to just define it as storage. So let's say it's a uint. Actually, let's create a nested array and just prove this whole concept works. It's going to make it private, and I'm just going to call it nested. Okay, so it is a nested array. Now, when we had that function call before to, for instance, nested 0, this won't work now. Because instead of that reference, we'll probably have the same issue we did before, because that reference point won't exist. What we need to do is we need to push our value onto our array. Because we're pushing an array onto our array of arrays, we need to state, let's just say 2 and 3. So now we can actually push a value to our array. Now let's just see this in practice working, just so I can prove that this is a valid way to do it. So if I call getArray, we're not getting any errors, everything just works and everything's nice. Now the only thing you'll probably notice is the very high gas execution cost, and that is because any interaction with storage is extremely expensive. Well, it's extremely expensive, it's quite expensive. Things can get a lot more expensive than this, and you generally don't want too many calls to the storage sort of variables if you really don't need them, and especially something like a nested array, because obviously if we cut this down to a singular dimensional array and then we create the same sort of contract, get array, we're basically cutting the actual execution cost by less than half, and we're only adding like 1 value to it. So that is something to be mindful of. I think even if I added the same, I don't know if I added 3 values to that, let's see how much that costs. Remember, this is 3 calls to storage versus that 1 we had. So even 3 calls is less than that 1 call that we made before. So again, be mindful of how you actually want to structure your data and store variables. Now, let's say that we are really at a bind and we really want to return a nested array to the user. Well, I'm going to show you a little technique that I know. Now, this is only using a single dimensional array because it gets quite complicated and very involved when I'm sort of like programming these sort of things. I'm going to be using like a little guide that I've already written myself, because actually testing this to get it working was a real pain in the ass. So what I have here is a very simple, in fact, I'm debating whether it's worth me actually showing you this example by me typing it out. What I'm going to do is I'm actually going to copy and paste this, because I feel like me typing this out is probably not going to help too much. I've got a lot of gists knocking around, and it's actually these 2 functions. No, that's the wrong function. There you go, data conversion, that's the correct function. Or the correct contract, should I say. And it's just these 2 functions down here that I want. Okay, so we have these now 2 functions. Now, what this essentially does is allows us to basically take an unsigned integer array. Now, I'm using this as an example because obviously this could be expanded to a 2-dimensional array. The only issue is that you'd have to have like a pass-through for this. So for instance, what I mean by pass-through is you create a function and calls like get data, and that is public and returns a let's just say it returns bytes, and that then itself calls this 2 bytes, return 2 bytes with, you know, your 2-dimensional array, so forth, whatever in there, or whatever that'd be, something like that, for instance. And then we can make this internal, and obviously we can pass 2-dimensional array into this, and so forth and so forth. But for now, I'm just going to keep it simple with a very singular sort of like 1-dimensional array. Okay, so let's get rid of all that. Now, what we have here is a bit of assembly. Now, because you can't really do this very easily without assembly, unfortunately I have to just do it with what I have with assembly. So let's just kind of have a quick look down at what we actually do. So the first things first, we define a value of PTR as the bytes that we're going to return. Now, the reason I'm doing that is because if you use the statement return within the inline assembly in Solidity, it actually kills the execution of the thing you're currently executing, which can actually be a pain in the ass if you don't want to return to the user at that point. So instead, what we're going to do is define PTR up here. We're going to first find the length of our uint array up here. Now, when we do an mload of the uint array, this automatically gets loaded into memory. So like previously mentioned, the first 32 bytes is actually going to be the length. So when we're loading this in, we're only loading 32 bytes. So that's going to be the length of our array. Now, the next thing we're going to do is assign the PTR to the position M size. When I mentioned before that we're going to move the pointer to the next free memory pointer, this time what we're going to do is go, please tell us where the next free memory pointer is, and we'll point our pointer to where that is. So we've just been told it's at 120 or hex 120. So we're now pointing our pointer down at the bottom here under the unsigned integer, which is fine. So that means we're not going to be overwriting anything. Now, the next thing we want to do is start storing some data of an array in bytes. Now, you could do this one of 2 ways. Now, I could simply state the length here. I've actually commented this out because I was playing with a few things while I was doing this. What you traditionally do is set the actual mstar pointer to be 32 bytes, and that's what this is here. And that's simply stating that the first 32 bytes are data type. Actually, that's incorrect because this is actually relative to the bytes. In fact, I don't need that line at all. So right, so what we're stating here is this is the complete length of the array. So what we're doing is multiplying the 32 bytes by the length of the array and 2. Now the 2 is these 2 values here, which is the 32 bytes which we had before of here, So we need to define 32 bytes for the data type and 32 bytes for the length. So that's what this is. So that's 32 bytes for the data type. Then there's 32 bytes for the length. So we need to know the length of the array plus 2 times 32 bytes, because we essentially need 32 bytes per value and for the length and the data type. I know it can get a little bit confusing, especially if you're not using a length of 32 bytes, but I'm just using it as 32 bytes just so I'm kind of universal with this. So inside the bytes now, we've stated the length of the bytes. We're now stating the data type of the array, which is our unsigned integer or 32 byte integer. Then we're stating we want to store in the next available byte the length of the array. And then what we're doing is iterating over the array. I've already highlighted how to do a basic iteration within assembly, and I'll leave that in the description box down below. And all we're doing here is basically saying, is the index equal to the length? If so, end the actual loop and sort of store the length or what we've actually stored against the free memory pointer. So remember, we need to set it after all our data has been stored, because if we do it before or do it in the wrong place, our data will get overwritten and we'll get garbage returned to us. So going back to the loop statement, all we're storing here is the value that was stored in the array at that relative position and mapping that to where it would be in our byte array relative position. And then simply at the end of that, we're incrementing our index by 1 and jumping back into the loop, and over and over and over again. So what I can simply do is take the actual value that I pass in. So let's, for instance, take an array here that I've already predefined. Let's create our nested array. Let's pass in this 2 bytes, because we're actually converting an array to bytes. And if we look at the details, we now have this value returned to us. It's a big long hexadecimal value, which is basically saying the first 32 bytes is the overall length. Actually, no, sorry. First 32 bytes is the data type. So that's going to be a 20 or 32, which is up to there if I'm correct. Then the next 32 bytes is the length of the array. Then which is 4, and then next 32 bytes is the first value of the array. Next 32 bytes is the second value, third value, and fourth value. Remember, we had 1, 3, 2, 4, so we have essentially 1, 3, 2, and 4. So that's all turned out right. Now, for instance, here you're not seeing the actual length of the bytes because it's already been assumed and it's actually been returned as part of the actual just length of the bytes. So we don't really need to do anything for that. That's more of what the virtual machine needs to know to return X amount of bytes. And that, in a nutshell, is just a simple way of how to return an array as a set of bytes. Now, obviously, you can expand this even more and do a two-dimensional array in the same sort of fashion, but it's a bit more involved. Like I say, I don't really want to go into this too much, because these whole assembly tutorials can get quite drawn out, and this is probably a long enough tutorial as it is. So the next thing we're now going to look at is the toArray method, where we're actually going to reverse this. So what I've done here is taken all these bytes, copied them up here, as you can see all along the top of this, and we've taken all the bytes all the way to the 4 at the end. So we can see somewhere along there we should be able to see the first, that's the 20. That's basically saying we've got 32, we're using the data type size as 32. Then the next thing value you'll come into is the 4, which is the length of the array, and so forth with all the values as well. So let's just copy that for now. And all we're doing is mapping it back to an unsigned integer array. Same sort of fashion, we got the bytes up here and we create a pointer to our array. Now we're getting the length of the array first by loading the bytes, or the position in the bytes, with an offset of 2. Now if you remember me saying, so that's position 1 and down here is position 2. So actually starting from the 0 there. So that's position 2. So we need to know that 4. So then we can load 4 into our length. Then once again we set the pointer to the next free available slot in memory. We store the pointer length at the very first value, like I previously mentioned when we were looking at how things are stored. The first data type is discarded if it's stored in memory or in the storage. We only need length and then the number of elements. So once we stored the length, we then do the same thing as we did up here, except we're doing it in kind of a reverse way. So we're moving the values from the bytes to the the values from the bytes back over to the pointer of our dynamic array, incrementing over that 10 times, and then obviously we're moving the free memory pointer to after all our data has been stored, just so we don't get any data conflicts. So if I now take the data from what I did up here, paste it into toArray, call toArray, we now get a return value of an unsigned integer array with 1, 3, 2, and 4, just like what we passed in. So there we have it in a nutshell. That's a simple way of being able to like sort of convert data types using bytes. So obviously if I wanted to send a nested array to this, I could, through bytes, convert the bytes to memory, and then store the memory. For instance, I could pass it to the storage engine. I could use it in memory because I can read and write to that those bytes fine. It's only writing, I can read from those bytes fine in memory, or the dynamic array in memory fine. I just can't write to it. So once that's all been done, we can then use that array inside our code wherever we want without problem. And that in a nutshell is pretty much where I'm going to wrap it up today. Like I said, this tutorial was a bit involved. There's going to be a document following this up. I'm already starting to sort of draft up this document. As you can see, I'm sort of going into very similar things before, where I talk about kind of using nested arrays and so forth. This will all be up on my GitHub repository later on. If you want to keep up to date with my videos, and I've got quite a few actually lined up, it's just finding the time to do them, because some of these tutorials take a little bit of time and effort to sort of investigate all the aspects of each bit, get plenty of testing in. Obviously I wrote all this code before coming along and doing this tutorial, so that's something I've got to prepare. There's a couple of key topics that I am going to do soon. I know I've said a few times optimization. I have a few ideas in mind now how I can simplify that, and then more smaller optimizations rather than big sort of let's rewrite everything in assembly optimizations. The next thing I also want, not the next tutorial, but another thing I want to look at is security. That's a big thing. I don't think I've really addressed pre-existing vulnerabilities, and especially I want to take a little page out of a few other people's examples when looking at security and vulnerabilities within Solidity, and especially having a look at what happened with DAO, or the DAO. Basically, that was a massive contract that got they lost so much money, and I want to try and help and educate to help people to understand how they lost the money, as well as ways that you can prevent similar things happening to you. So that's a big topic I want to cover, and there's a few other little bits and pieces of topics I want to cover. Now obviously keep an eye on my GitHub, and I'll keep that up to date with the latest support sort of documents or articles that I put together. They might always not be coherent. They might be like the early drafts, like the one I've just posted today's probably got a load of gibberish in which I need to fix. You know, I was up to I think about 3 AM trying to get that thing finished, just so I can actually get it working sort of like a proof. And yeah, so that might be a bit sketchy. Now if this video did actually you did find this video useful, feel free to give it a thumbs up. If you'd like to stay up to date with all the latest content I have, hit the subscribe button and you'll get notified anytime I release a video. Other than that, if you have any questions or comments, feel free to leave them in the description or the comment box down below. Thank you for all the great feedback I've had. I really do appreciate it. If you obviously want to follow me on GitHub, obviously again you'll be notified anytime I add any content to that or make any changes. If you want to add any pull requests, I'm very open to pull requests. I will probably merge most of them as long as they're actually relevant. And yeah, again, thank you, and I hope you found this video useful. But until next time, good luck, and I'll catch you around.